Okay, thank you for the introduction. I'm Symeon or Akis Papadopoulos from CERTH UNINA in Thessaloniki, Greece, and coordinator of the vera.ai project. And together with Luisa, we will try to give you an overview of the landscape of synthetic media detection. I will start with a few introductory words about our project. Then we'll provide some background information and some motivation about the problem of synthetic media detection. And then I will hand over to Luisa, where she will give an overview of the methods that we built in vera.ai to tackle this problem, and of course some of the open challenges we face. Of course, any questions, you can write them in the chat, and we will take them, I think, in the end, or of course, if it's possible to ask something, that's feel free. So first, a few words about our project. This is a Horizon Europe project that brings together 14 partners across Europe, and EBU is one of them. There are both research partners, universities, as well as companies and civil society organizations, and of course, journalistic media organizations. And we come together to build trustworthy AI solutions with the goal of fighting disinformation. And these methods and tools that we built, we try to bring them to the hands of media professionals, journalists, and fact checkers. vera.ai is a quite ambitious project and tries to offer a very wide range of solutions, and also to perform computational social science research around this information. But for this webinar, we focus on the part related to the verification of multimedia content. And more specifically, as one of the objectives of the project, we aim to build AI tools for the detection of deepfake, synthetic media, and manipulated content. And these include things like detecting deepfakes and different types of video forgery, detecting fully synthetic or partially manipulated images. And I will give a bit more details about what, in general, synthetic media means and how we classify it a bit later. But some common challenges in trying to build such tools is that we want them to be fair, transparent, also explainable, robust to new kinds of generative models, and to be able to adapt easily to the quickly evolving landscape of generative AI. The methods that we built are based on cutting-edge AI research. Several of us in the consortium are conducting research for several years in this area. But from the research lab to the actual usage of these tools, there is a lot of effort to be spent. And within Vera, we try to really work together directly with end users like journalists and fact checkers to integrate our research into usable tools. And within the project, we have the so-called verification plugin, Truly Media, the virtual assistant, and the database of known fakes. And we try to bring our results within these tools. In addition, we are also at the second level in direct connection with several initiatives across Europe, such as the European Digital Media Observatory, EDMO in short, and also several EDMO hubs across Europe, where several of our results are disseminated there via events and also via several reports. And also there are other relevant EU funded projects like AI for Media and AI for Trust that we have synergies with, the AI on Demand platform, and initiatives like the European Language Grid. Perhaps the most well-known tool from our project is the so-called verification plugin. This is a tool that is mainly developed by our partner AFP, the French press agency, and development started already in previous European funded projects and continues in vera.ai. And even though this tool brings together a number of utilities and more sophisticated tools that are helpful for verification, we are now focusing in integrating our synthetic image detection and deepfake detection. More on that you will learn in the next slides. And we bring this to the hands of really many professionals, since the plugin is currently used by more than 100,000 users worldwide. And the second tool, which is a commercial tool developed by our partner ATC, is also integrating the results of our research in offering access to synthetic media detection services, and also making it possible to use this in a more collaborative environment that teams of journalists and fact checkers are used to work with. Just for your information, this is an event, Meet the Future of AI, that our consortium organized together with other relevant projects, both last year and last summer, so in June 2023 and 2024. And you can find several of the findings of this event in the website, but it's also worth reading a white paper coming out of this event, which is still, I think, a relevant report that summarizes the state of the art in generative AI and disinformation. Now let's move on a bit to the problem of synthetic media and disinformation. It's worth mentioning that even though disinformation has been recognized as an important problem even since 2016, the latest World Economic Forum Global Risk Report has ranked disinformation as the top global risk for the next 2 years, and as the fifth risk for the next 10 years. This is based on the input of more than 1,400 experts worldwide who monitor a number of risks. I think we all recognize that disinformation can really exacerbate existing tensions and polarization that we see worldwide. And I think the recent surge of generative AI is also contributing a lot to the growing concern about disinformation. Synthetic media is nowadays ubiquitous and it's growing. It affects all kinds of media, so from simple text, so news text articles, synthetic audio, images, and videos. And we've seen during the past year a growing number of cases where synthetic media has been used in the context either of propaganda or political disinformation, or even for plain manipulation. A very interesting recent research by Google, DeepMind, and Jigsaw researchers has investigated and analyzed more than 200 cases of generative AI misuse, and it presents a classifications of them, and I think it's a very interesting read. Among the most common cases of generative AI misuse have to do with impersonation, scaling and amplification of messaging, falsification, sock puppeting, and appropriated likeness. And these are all heavily related to disinformation campaigns and propaganda. And also there is an analysis on how frequently each modality is used with each type of misuse. And we can see that visual content like images and video, but also audio, is heavily used in conjunction with malicious attempts to use generative AI tools. And for that reason, I think it's obvious that we really need powerful detection methods. Also, as an example of the grave impact of disinformation, here we see a synthetic image of an explosion outside the Pentagon that circulated on May 2023. Even though this was relatively quickly debunked, it was sufficient to create quite considerable change in the S&P 500 index. So it means that some people could easily profit from quick trading if they knew that this was fake. So we can see that such media can have a really important impact even in monetary terms. Within vera.ai, we have also, with the help of our partner AFP, conducted an analysis of existing fact-checked deepfake cases, and have indeed found that the large percentage of such cases aim at spreading propaganda, either political propaganda or war propaganda, or political disinformation, health disinformation, and other kinds of harmful content. So it's a very well recognized risk, and there is a very growing number of such cases circulating the web. In order to better understand what synthetic media is and what we can do about it, I think it's useful to think about some dimensions of synthetic media. First and most obvious is the type of media that is generated, and this can be, as we said, text, images, audio, and video. Then it is useful to distinguish between the different extents of manipulation. So some of the AI-based manipulation can happen at a local or regional level. So parts of the image or parts of a video can be changed, or we can talk about completely or fully synthetic image and video or audio generation. Then it's very useful to know a bit about the generative model that has been used to create the underlying media. And in the case of image and video content, the most prevalent models are the so-called generative adversarial networks, GANs in short. This was the first type of model that was successfully used for realistic image generation. But nowadays, the large majority of models are based on the so-called diffusion models. And this is by far the most popular method today. There are also some very emerging and promising approaches like neural radiance fields, nerves in short, Gaussian splatting, but there are also still several hybrid approaches and even more traditional computer-generated imagery techniques. And another dimension that is important is the kind of semantic modification, the type of semantic modification that such synthetic media experience, and this can range from face identity swapping to attribute editing, reenactment, and lip syncing, and the like. Another important aspect of generative AI is the level of control it gives to people or actors who want to generate media. In the early days of synthetic media, the input was random noise, and this essentially gave almost no control over the generative process. So you essentially got a randomly generated image each time you run the model. Very soon, there were some advances in how this generative process was controlled, and it was possible to use the so-called latent space of generative models in order to have a level of control, for instance, starting from some example images to try to create generative images that looked a bit like this or shared some attributes. But nowadays, a very common control mechanism is the text prompting, and I think the majority of modern generative models support text description as an input to the process. But there's also more fine-grained control, like providing an input image and describing in text what kind of changes someone would like to have. I think it becomes obvious that the more control that these models offer to people, of course, in positive applications, it unlocks the creative potential of people, but for malicious uses, it also increases the risk and the possibilities of creating harmful content. And at the same time, over the years, we've seen remarkable improvements in the output quality of such generative models. And here I show two examples. In the first case, how the image quality evolved in the generative adversarial networks. The first one appeared in around 2014, and you see that it was very low resolution, very low quality, and even black and white images. And in a matter of 4 or 5 years, such models could depict very realistic human faces. And a very similar situation also in the case of diffusion models with Mid-Journey, which already is now in version 6.1, and you can see impressive improvements starting from version 1 to version 6 in the course of less than 2 years. And these are just indicative examples. There are really many impressive advances also in deepfakes and in synthetic video. There is also a very big growing market of synthetic media tools and services. Some of them are very popular, like Stability AI, Mid-Journey, the recently released Flux.1, Imagen 2 and 3 by Google, Adobe Firefly, and several others. It was estimated that last year more than 15 billion images were generated using such services. So you can imagine that this is only growing. So we are flooding in a massive sea of generated content. And just before closing my part and handing over to Luisa, we need, as I said before, powerful tools for detecting generated media. And a very typical approach in machine learning is that we start from a so-called training set, which consists of real media and AI-generated media or AI-manipulated media. We try to train typically a very deep neural network architecture in order to come up with a detector. However, this very simplistic view is hiding several details, especially how we form the training set, how we get access to training sets that are up to date and representative of what we see in on the internet. how we train the model. There are many different architectures, there are many different approaches to training such models, also computational consideration aspects, and of course deploying the detector in the wild and also providing support to end users of such detection tools is also a crucial aspect. With this in mind, I would like to hand over to Luisa, who will provide many more details about our research in vera.ai. So I will stop sharing now and will ask Luisa to take over.
Okay, can you see the slides?
Yes, but not in yes, in full screen mode now.
Okay, okay. So thank you, Akis, for this very nice introduction. I will go more in the details of the technical solutions that have been designed in the veraAI project, and we will start with this synthetic image detection. In particular, in this slide, you can already see a difference between what is typically known as fully synthetic image, so an image that is completely synthetic as the one that you can see on the right, and these are typically driven by text, by a prompt. So you have like a sentence, like the ones that you see in this slide, a monkey eating a banana or recorded in a field, and you can generate an image. And of course, you can imagine in the wild other images that we are showing in these slides that can be generated and are also very much realistic. Of course, it depends on how the training data were used in these generators, but you can see that popular and well-known people are very well represented in these images. Beyond this type of images, you can also modify only a part, only a region of the image, and you can see this on the left. So these are like local synthetic manipulations. So you can just ask the software to modify one part, and you can also, define what you want to see in that specific region. And we will start with this type of manipulations in this presentation. So here just an example of what you can do using Adobe Firefly, which is a software that can be used by everybody. So this is an image from Naples, my city, and we just we just selected the region in this image, and then there is a prompt. So this is a sentence, a tank and Ukraine flag. And in a moment, you can modify it. This is something that is really, great in the sense of what you can do in terms of manipulating an image nowadays is really very much advanced compared to what you could do 10 years ago, but even 5 years ago. When I started working in this field, it was so hard to manipulate an image and to take care about the perspective, the illumination, and whatever. And now it's just one click and you can manipulate an image. So one objective in the veraAI project was to develop interpretable and reliable approach for synthetic manipulation detection and localization. So this means that if we have an image and we want to provide a final score, which actually is related to the probability that the image was manipulated or not, but we also want something more. We would like also to know which part of the image was manipulated. And this is actually, so we want to work on this detection, so giving a score, a global score, and localization. So we want a heat map that is actually telling us which is the region of the image that was probably most likely manipulated. And what we found as a as an issue for the state-of-the-art approaches was that the localization of the manipulated images often gave rise to false alarms on real images. So actually, you can find a lot of methods in the literature that localize manipulations, but most of them then tend to give a false alarm on pristine images. And so we wanted to work especially on this aspect, and we developed a method that tried to, given a test image, extract and analyze a noise fingerprint. So you can see here this noise extraction. So as Akis highlighted before, I mean, these images are really very realistic. So you cannot really perceive inconsistencies or, you know, some specific artifacts, some visual artifacts. I mean, they are really very well done. So the idea was to extract some hidden artifacts. And this is very common in our research. So trying to extract artifacts that are invisible but are present inside the image. And you can see here in this image that there are some inconsistencies in the noise level of the image that are not visible but can be detectable. And after that, so we wanted to localize the manipulations, but we also wanted to reduce the false alarm. So you can see that in this localization map, there is a false alarm on the bottom. And so we tried to estimate what is called the confidence map. So a map that is actually helping us to understand which are the region of the localization map that can be more reliable. In this way, we can obtain a global score that is influenced by the confidence map and help to reduce false alarm. And I will show you an example here. So for example, you have a localization map for the fake image, which is, as I've shown to you before, quite good. I mean, you have only a small false alarm on the bottom, but for the real image, for example, you have that a very high region, say very large region that actually is labeled as fake. And the confidence map can help us to modify the final score. And so you can see that, okay, for the fake image, we were already good, but for the real image, the score was higher than 0.5, which means, okay, it's probably it's manipulated, while using this confidence map, it is labeled as real. So this was something important in our project to the development of this confidence map, and this is actually the first work in the literature that is promoting this type of strategy. And I'm just showing to you some other examples that were created using Adobe Firefly. So we have the authentic image on the left on the top, and the manipulated one, where you can see the manipulated areas, which are highlighted in yellow. Then the localization map and the confidence map. In this case, everything is fine. I mean, the image are correctly identified. But I also want to show you something more that you can do using this AI generative tools. Here is the AI generative expand tool, where you have on the left the original image, and in the middle you have the manipulated image. As you can see, the image was enlarged, so it was made bigger, and it's actually it's very difficult to understand that the created area was fake. And I just wanted to show you that in this noise print, this noise inconsistencies we want to highlight, you can see a very interestingly that these two parts can be visually, you can visually notice the inconsistency. So you can I'm highlighting that there are these inconsistencies that is invisible to the eye, but can be extracted by our tool. And of course, I mean, this method is not perfect. It was published last year, and of course, it can be improved. In particular, we noted that there are some failure on very uniform or saturated areas, like in this type of images, and we are trying to retrain our approach in order to reduce possible problems. Okay, let's now go to the fully synthetic images. Of course, in the wild, you can have everything. And right now, we do not have a single tool that is able to detect everything, but we have several detectors that can handle some specific cases. For fully synthetic images, first of all, I want to show you again these low-level forensic artifacts, not in the spatial domain as I've shown to you before. This is actually the frequency domain. We will not go specific into the details of the technical details, but just want to show you that in this image on the bottom, you can see that for each synthetic generator, there are different traces, different artifacts. The first image, you can see the image that is real, and you don't see any type of specific inconsistencies or specific traces, while on the right, for each synthetic generator, you can notice these very strong peaks that are related to the synthetic generator that was used for the generation. And you can see that, first of all, these are different. So this actually highlights a very important problem in our field, which is if you train, I mean, Akis showed to you the basic basic pipeline where we try to train on very large data sets of synthetic and real images. So if you train on a data set of fake images with specific generators, for example, Big Gun or Style Gun T, then it's very hard to generalize on other generators. And so if these traces are similar, then it's fine. Otherwise, we can miss the detection, and this is a big problem in this field. So, for example, what we noted that Midjourney has very similar traces with latent diffusion and stable diffusion, and this is the reason for which our detector that is in the platform, that is available in the platform, that was trained on a very large data set of latent diffusion, can generalize also to stable in Midjourney. Of course, this does not ensure that it can generalize to every type of synthetic generator, but I mean, okay, sorry. But of course, I mean, it can, these fingerprints, these traces can in any case help to interpret the results. And for example, on a data set of Midjourney, the Midjourney v5 traces correlate very well with stable diffusion models, and without retraining, we could obtain very good results. However, I mean, there is a very recent paper that was developed by the researchers from CERTH, from the group of Akis, and this actually have shown that if we look not only at the low-level visual information, but we also look at high-level information using a very recent model it is the CLIP model that it was pre-trained on a very large data set of images and also text. I mean, this actually presented very good features in terms of generalization. So even training on a specific synthetic generators, which is the ProGAN, it was very good also to detect diffusion models and other type of GANs, and even DALI2, Firefly, and Midjourney. And this was actually a very good result, and also this type of synthetic detector is present in our tool. One shortcoming is low performance on high resolution in the wild AI generated content, but I have to say, and we will see later, that high resolution in the wild is also not very likely to appear because images are shared over social networks and often they are low quality. We also work on the deepfake video detection. So Akis already told you that the faces can be manipulated in different ways. So you can swap a face into another, or you can only change the expression, you can only change the speech, the audio. And we actually, here I'm showing to you some examples of different manipulations, like swapping, and in the first case, face-to-face instead is just modifying the expression of the video. So you can have different type of manipulation. the target video is the video we want to manipulate, and the source video is the video we are using to create the manipulation. And we actually worked also on basic classifiers that were trained on large data sets of fake and pristine videos. And it seems that the results were very good in terms of accuracy, but we noticed that, and also in terms of localization, I mean, you can see these maps are perfect. The main challenges also in these cases are robustness. So we get worse results on low quality data, and false alarms can arise in the localization map. And again, generalization. So if we train on a specific type of manipulation, the accuracy is very high on the same type of manipulations, but can be like random guess on a different type of manipulation. So the robustness and generalizations are really the most important challenges in this field. And so what we decided to do is to change the paradigm, and without trying to understand if the video is manipulated or not, so looking to forensic inconsistencies, we moved to this other type of problem of question: is this the person who is claimed to be? So we are actually trying to understand if the person still have the same biometrics and the same biometric traits of the person of interest. So we are more trying to understand if the video under test belongs to the real videos of the person of interest, which is something that we've done in the last year, in the last 2 years, which was trying to first work in a multimodal setting, so trying to exploit both audio and video analysis. And then we train only on real videos, which does not include the person of interest, and this actually ensures generalization. And so our approach is actually working on training on not videos that are almost 5,000 real identities. So we are not training on fake videos, so we are not like adapting to a specific type of synthetic manipulation, and it exploits both audio and video. And this is an example that we actually have done on this video from Putin, where we have a constraint, since we require about 10-15 pristine videos of the person of interest during the test, during a test time. And you can see here on the right, you can see the distance that we are evaluating from the video under test and this reference set of videos, and these distances are all above a certain threshold, which is the red line that is actually set in advance on a specific validation set. And we also worked on synthetic audio detection, and here we have a slide that just showing to you some example how it's easy to generate such audio. Synthetic audio, probably it's not working, right? The audio, even if I shared it. Okay, maybe I will check after if I can show to you some synthetic audio. And the technique that was developed by IDMT from Fraunhofer, it's really interesting because it actually tries to exploit some specific features from the audio, like the melody of the voice, the color of the voice, how vowels are pronounced. And this is very important because we aim to develop explainable methods. So methods that can be, that we can explain to the user. And here now it comes from the open challenges, which are essentially challenges about integration, detection, accuracy, and reliability, and now the fully synthetic videos. Let's go deeper into details of this. So one problem I already highlighted, this is the robustness and stability. So whenever you go over the web, it's very hard that you have videos that, or images or audios that are high resolution, are very good, very high quality. They're often resized and compressed several times, so the traces can be reduced. Then one challenge which is really important is how to communicate the result to journalists and fact-checkers who don't have the technical background. So they often ask, how did a certain percentage come up as a result? Can we attribute to a specific generative model the image under test? And so, I mean, this is really very important, and it's very important that we are able to explain the results. And I mean, this is also something that we want to show you, and it's related to a recent work done by CERTH with also France Press, which actually is saying whenever we download images from the web, there is actually the original image, but a lot of derivative images. So these images were probably, as I told you, not only compressed, resized, modified, some text was overlapped on it, and you can see, I mean, the original image was, you know, modified. And this poses another challenge because it causes a lot of several false positives or misdetection. And in this recent study that was done by Akis and other researchers, they showed that considering only a subset of base synthetic images collected in the wild, the average performance could decrease by 6% in terms of AUC. And also here you can see, I mean, the famous pop image where from the initial sharing, over time, the image was manipulated several times. And also in these cases, you can have a drop in terms of performance. But if you retrieve the early versions of the image, so the version that was less modified, you can have an increase of performance of around 8% on average. And finally, I mean, just want to show you recent videos from generative AIs that are like the ones that were like developed using Sora. I don't know if you have seen over the web. I mean, the quality is really impressive, and we are currently working on these videos since, I mean, they are really well done, no visual artifacts, and it's very challenging to detect them if videos are on the web, so they are strongly compressed or resized.